Okay, good morning, everybody. I guess I'm about a lecture behind, but I think we'll make up a good bit of it because the last set of notes that I had gave room for catching up. Today, I want to spend most of the three lectures talking about metal combustion, how metals are added to energetic materials, the interest in going to nanoparticles, and then looking at some of the pyrotechniques, intermetallics and metallics. But I did, if you remember from yesterday, I was showing you some interesting movies comparing nitromethane and hydroxyammonium nitrate as liquids burning at very high pressure. I didn't show you this plot here. And again, one of the important differences between the two, nitromethane and hydroxyammonium nitrate, is over the pressure range that I showed you for nitromethane, there's no condensed phase reactions. If you were to take pressures up to gigapascals, then nitromethane will have some condensed phase reactions. But in the case of hydroxyammonium nitrate, it has a condensed phase reaction from ambient pressure all the way up. And so the one thing I did plot here are some critical temperatures as a function of pressure. And what you'll see then is the violet circles are basically the decomposition temperatures of the hand. And what's plotted then in the dash line and the solid line here at the base are the boiling point temperatures of both the methanol and the water in that solution mixture. And you can see the decomposition temperature of the hand is below the boiling point temperatures, which means you're going to be adding heat directly to the solution, and that's how you're going to be brought to the critical temperature, which is significantly different than in the case of the nitromethane, where the way I'm brought to the critical temperature is from the energy from the gas phase reaction being conducted back to the surface. Okay. Okay, so as I said, what I want to do is move on to the next set of notes. Okay, so this is a very interesting plot in itself. So historically, what I'm showing you here is essentially detonation velocities of organics. These are some of the energetic oxidizers that we've been talking about. And you'll notice that in terms of detonation velocity, which is basically energy storage that we're able to put into the organic material, we're starting to reach an asymptote in terms of discovery of new molecular structures. And recognize that all these structures are based on carbon, hydrogen, oxygen, and nitrogen. And so, one of the questions is, well, how can more energy density be added to the material itself? And obviously the propulsion community recognized this years ago when they started to add metals to propellants. These metals were typically on the orders of microns in size, and usually too large then to couple directly to a detonation. So, they had a little bit lesser value in explosives, although if you're looking at, depending on the characteristic time of the reaction you want in the explosive, they did have some use. So what's been happening? As I said, increased sensitivity correlates with increased energy density. So one of the areas that's had a lot of concentration in recent years is basically nanoengineering for manipulation and control of energy release rates. And one way to do that, as I said, is to consider how I can make use of metallics. So this is a plot you'll find often in terms of looking at energy availability of different metals. And what's listed here in this bar chart is the heats of oxidation based on both a gravimetric basis and a volumetric basis for a number of metals. And you can look at the far right, and I'm comparing it to hydroxyl terminated polybutadiene, if it was oxidized in pure oxygen, and JP4. So what stands out right away is basically boron and beryllium. I will talk a little bit about boron, but most of the discussion is going to be on aluminum because it's the more popular. Boron particles have had some difficulty in propulsion systems. And you'll see that in a little bit. They're very difficult to ignite, and to capture all of the energy out of the usage of boron, you've got to form certain molecular or condensed phase species in the products. So anyway, based on a volumetric basis, you can see that aluminum's very appealing. The beryllium had been used years ago, but it's toxic, so it's not being used anymore. And some of these other species or compounds, as I move to the right, the molecular weight starts getting too high for usage in propellants, but they do have usages in explosives. So the two common ones are aluminum and boron. And what you'll see, which is driving the interest in nanomaterials, is that the combustion of micron-sized particulate metals typically diffusion controlled, and the combustion times are long. So to shorten these times, investigation of nanomaterials as energetic materials has become of interest. Okay, so the first thing I want to do is just give some thermodynamic understanding of how metals burn. And this is going to pertain mainly to large particles, so tens of micron, and then we'll start looking at what happens as we get to smaller particles. But looking at what thermodynamics can tell us first. Okay, so the determination of which metals will burn in the vapor phase or heterogeneously can be made from knowledge of the thermodynamic and physical properties of the metal in its oxide product. The oxide products are typically refractory, and they have very high decomposition or vaporization temperatures. Typically, the boiling points of the metals are high as well, compared to, obviously, to liquid hydrocarbon fuels. For oxygen-containing environments, early studies recognize two important factors: the importance of the volatility of the metal versus the volatility of the metal oxide. And that's typically going to determine whether or not the metal vaporizes and that metal then diffuses away from the surface, mixes with incoming oxygen, and I have a detached flame away from the surface. Okay, or whether or not the oxidizer diffuses all the way down to the surface of the particle and reacts directly with the condensed phase. Okay, and then the second important relationship was between the energy required to gasify the metal or metal oxide and the overall energy available from the oxidation reaction. And this comes about and actually can limit the flame temperature itself. Okay, and by what I mean there is if I look at Q sub R here, that's the amount of heat being released from the oxidation reaction of the metal. Okay, and then it forms a product. And that product has to be heated up to the combustion temperature. Okay, so there's a term here, which is essentially the sensible enthalpy, the C sub P dt term of bringing that temperature up. So if I take the difference between those two, that's the available energy I have to dissociate or vaporize the metal oxides that's been produced. And often what you'll find then is that this energy here that's available is not enough to completely vaporize or decompose the metal oxide. So it remains in a condensed state. So to kind of show you that, this table presents those boiling points and enthalpies that I just mentioned. So looking at the metals going down, the first temperature is the boiling point of the metal. The second identifies the final oxide product, or the third column. And then the fourth column is the volatility or gasification or decomposition temperature of the metal oxide. Most metal oxides don't basically just vaporize and form that oxide in the gas phase. There's a few that do that, but most of them decompose upon vaporization. Okay, then the next column is essentially the heat of formation of the oxide, which is really going to be the heat of reaction then if I write it for 1 mole of formation of that oxide. And then the second to the last column is the necessary C sub P dt term to basically bring it up to temp. Well, the second to the last term is the change of enthalpy necessary to basically bring it to volatility, and then the last column adds the 2. Okay, so as an example then, if I look at aluminum, the first thing you note then is what's the boiling point temperature of the metal. It's like 2,800. If I look at the decomposition temperature of the oxide, it's 4,000. So this is going to tell me right away that it's highly likely that aluminum's going to burn in the vapor phase, okay, because it has the lower melting temperature and boiling temperature for the metal itself. If I come over to the right-hand column then, the heat of release from that reaction is minus close to 1,700 kilocalories per mole. But basically, the amount of energy I need to completely dissociate and bring the oxide up to that temperature is greater than that which is available. And as a consequence, then the flame temperature is going to be limited to basically the gasification temperature of the decomposition. And I can go down this list, and if you look at boron, for example, boron has a very high vaporization boiling point temperature for the metal itself, and the boiling point temperature for the oxide is considerably lower. So this temperature here is very close to the vaporization temperature of, say, carbon. And if you know anything about carbon oxidation, it basically burns as a solid. Okay, so in this particular case, boron is going to burn heterogeneously. The oxide is going to come to the surface, react in a heterogeneous reaction to make suboxides. If I go down further, all the ones that are in tan are basically going to typically vaporize and burn in the vapor state, and those that have no shading will be burning heterogeneously. Okay, and if you go over to the right and compare the energy that's been released here to what is necessary to completely decompose the oxide and raise it up to the temperature, you'll see that many of them are going to have limiting flame temperatures as well. So let me show you this in a little bit more graphical form. This is just some equilibrium calculations that you learn in combustion, okay? And so what was taken here is a stoichiometric mixture of aluminum with oxygen, the initial temperature 298 Kelvin at 1 atmosphere. Okay, and so what I'm plotting is the equilibrium mole fractions of the species and the temperature of the reaction, the adiabatic flame temperature. The term 0 here means that all the enthalpies in the reactants were at their correct standard conditions. So if I were to do that calculation, what I would find then is the adiabatic flame temperature for this reaction would be close to 4,000 Kelvin. And if I looked at what was in the products, I would see that about 20% of the products was liquid aluminum oxide, and then another 30% was atomic oxygen, maybe 25% aluminum monoxide, etc. But what I show in this calculation then is suppose I remove enthalpy from the initial reactants, or suppose I add enthalpy. You can think of the idea if I remove enthalpy, it's like a heat loss in a real problem. So if I start taking enthalpy away from the initial mixture, notice the flame temperature doesn't change. It's being limited by the fact that I've still got gas phase species and liquid phase species together. Okay, so it's sort of like going across the vapor dome of vaporizing water, right? The enthalpy of vaporization. So finally, if I take away enough heat or enthalpy, then all the gas phase species go away, the temperature can now drop, and I only have condensed phase aluminum oxide in the mixture. If I add enthalpy to the mixture. I continually add it till I add enough so that I completely vaporize all the aluminum oxide. And then the temperature is free to go up because it's no longer restricted, and the gas phase species basically go up too. You see more dissociation. Okay. So that's the concepts of a limiting flame temperature, and also we'll see the fact that whether or not I have a vapor phase flame or a heterogeneous reaction. So the same thing can be seen if I do a nitration of the metals. So this is looking at a reaction of taking aluminum with molecular nitrogen, reacting them, and looking what forms. And you can see again a limiting flame temperature is formed. The major product here is aluminum nitride in the solid state. But if I remove enough enthalpy, I get to the state where there's no gas phase species and the mixture is all aluminum nitride, and vice versa if I add enthalpy to the system. Okay, now if I look at boron, remember boron was one of the cases that did not have a limiting flame temperature. And so the standard state condition is over here. So if I do my equilibrium calculation, I find the predicted temperature would be about 3,700 here, and what's in the products is BO, BO2, O2. So they're all gas phase species, and the B2O3 is basically very small, but you can actually have a gas phase component here for B2O3. If I start taking away enthalpy, I'll eventually get to the point where the B2O3 in the gas state starts to condense out, and then I'll see my limiting flame temperature. Okay, so this table here sort of summarizes in the types of modes of combustion that one can have of a metal and how you might break it apart. And the first question is whether or not the product is volatile or non-volatile. Okay, so in the case of the boron, it had a volatile product. In the case of the aluminum, it had a non-volatile product. And then you can see whether or not the metal itself is volatile or non-volatile. So in this particular case here, the non-volatile metal would have been boron combustion. So I have a surface reaction. I form B2O3 in the gas state, or it's decomposed. If I have both a volatile metal and a volatile product, then that's more like a droplet combustion. Basically, they're both burning in the gas state, and I don't form any condensed phase products. If I look at the case over here where I have a non-volatile product, but I have a volatile metal, this is gas phase combustion, so this would be like aluminum combustion. And on the right case, if both the product and the metal are non-volatile, then that's a condensed phase reaction. Okay, so the reaction is going to have to diffuse the metal and metal oxide through the condensed phase, and there may be some interfacial type reactions. And then you can actually break this classification down further, and whether or not the product that you're forming is going to be soluble in the original metal or not. And if it is, then you can see different types of characteristics happen during combustion. Because of phase diagrams, if I start to condense or some of the metal oxide starts to go into solution of the metal, you'll find as the characteristics of that change, you can actually have disruptions of the metal as it burns. Now, most of that was that atmospheric pressure that I was talking to you about. What happens if the pressure changes? And so obviously things like the vaporization temperature of the metal changes, and so do other physical characteristics. So this is an example where I'm looking at a aluminum combustion again, but now I'm looking at it as a function of pressure. So the case I just looked at was the 1 atmosphere case, and this solid line right here is the aluminum vaporization temperature. And this temperature right here corresponds to the aluminum burning in essentially air. So you can see the aluminum flame temperature is like 3,600, and the vaporization temperature of the aluminum itself is like 2,700. So I'm going to have heat feedback from the gas phase flame that's vaporizing the aluminum, and much like a hydrocarbon droplet, then the aluminum is going to vaporize and diffuse outward. But notice what happens as I go to higher pressures. If I continually go to higher pressures, eventually I'm going to see that the boiling point temperature of the aluminum, or its vaporization temperature, rises quicker than the flame temperature itself, and eventually they'll cross. So now when I'm out here, the flame temperature is less than the vaporization temperature. So now there's no way to basically, from that heat release, to basically vaporize the original metal. So it's going to start turning into a heterogeneous reaction. So notice if I were to oxidize or burn the aluminum in CO2, which would be an example if I wanted to do it on Mars, or if I wanted to burn the aluminum with water, which may be for underwater propulsion, then those temperatures, those pressures occur at a much lower value. So looking at the case here where I'm basically reacting the aluminum with water in the liquid state, you can see not too much above 1 atmosphere, I'm going to have that crossover point. And so I'm going to see the system change from a vapor phase reaction potentially to a heterogeneous reaction. And in the case of CO2, it crosses over here, so maybe at about 7 or 8 atmospheres, I'm going to see that switch over. So here's some actual experiments in which the ambient was changed. So in this particular case, there was an experiment that had a spool of wire of aluminum, and the wire would basically be turned, and it went through a little chopper mechanism to make little cylinders of aluminum before they fell. And as they started to fall, they went through the focus of a CO2 laser that heated up that cylinder and ignited it. And so that's what you're seeing here. The left-hand picture is the aluminum burning in air. It gets ignited. When I ignite it, the cylinder melts and forms a sphere, and it starts to fall in a low Reynolds number situation. And you can see then the combustion process. This is the original particle, the aluminum, and out here is where the flame sits. So the aluminum's vaporizing, it's diffusing outward, there's oxygen out here, it's diffusing in here, and I have a typical diffusion flame. The difference is you can see I'm forming smoke particles out here, which is nanoparticles of aluminum oxide in the flame zone. Okay, so what happens when I switch it over to water at atmospheric conditions? Well, right away, this is steam, and you can see I'm not getting that detached flame. What's happening is the flame, if it's detached, is very close to the surface, and these bright spots are basically ejection of aluminum oxide from the surface, because it's gathering so much on the surface, it's basically coming off as you react. On the right case is showing you the effect of pressure now in air. So compare this 2 atmosphere case with the 1 atmosphere case, and you can start to see already the flame standoff position is moving closer to the surface, and by the time I get to 60 atmospheres, it's almost on the surface. Okay, and if I were to go to higher pressures, then it would be completely on the surface, and I would have switched this vapor phase reaction to a heterogeneous reaction. Now, we did do we tried to get temperature measurements around a single burning aluminum particle. These particles are about 200 micron in diameter, and we used basically planar laser-induced fluorescence to do these measurements. However, we could not use a thin sheet because of the smoke that was being formed, and that scattered basically the radiation, and so we didn't know where the LIF image was coming from. And so what we had to do was widen the pump beam so that the entire particle was burning inside it, and we had to assume spherical symmetry and do Abel inversion, an onion peeling inversion technique to get the radial profiles. Okay, so you can see in this plot right here, which is normalized radius from the particle surface, and a plot of the species that we measured, which was aluminum monoxide. And you can see it basically evolves from the surface, grows to its maximum value off the surface, and then starts to be consumed as I move further and further away from the surface. So it's going to be one of the initial major gas phase species that are formed during the oxidation process. Now, what we did was we pumped the ALO at two different wavelengths or frequencies, and we did a Boltzmann calculation to see if we could back out the temperature. And indeed, the red symbols here are the temperature, and you can see it's very close to the 3,600 to 4,000 Kelvin where you would expect it. And what's typical here is you can see that in a hydrocarbon flame, this temperature profile would look more like the ALO, more peaked. Whereas in the aluminum combustion, there's a little bit of a plateau there because the flame temperature is being limited over some equivalence ratio or across the flame. Now, the other thing we did was, as this aluminum particle was falling, we put a silica wafer and we disrupted the burn process. So the particle falls and lands on the silica wafer and quenches itself, okay? And the goal was that initially it's this spherical three-dimensional image, and as it quenches, it forms a two-dimensional image of that three-dimensional structure. And that's what you're seeing over here to the right then. So here's the quenched particle on the silicon wafer, and all around it then is the smoke. And again, what we did was we did electron probe microanalysis every few microns, and we got the aluminum to AL, the AL to O ratio as you move in, and from that we were able to back out what the Al2O3 concentration might have looked like. Okay, and this just shows the quenched particles as a function of pressure. And again, you can see at 2 atmospheres, I still have this dark zone, but once I go to 10, 30, and 60, the oxide just rolls off the surface when it's quenched. Okay, and from those measurements, one can also get burn rates. In a diffusion mode of combustion, one should expect that the burn rate should be relatively independent of the pressure, because if you have studied combustion and you've studied droplet combustion, and there are some notes at the back of the note, you'll find that the burning rate scales with rho, the density, times the diffusivity, the log of 1 plus the Spalding B number. Okay, and the Spalding B number is only weakly dependent on pressure. Rho is directly dependent on pressure, but the diffusivity is inversely dependent on pressure, so rho times D cancels out the pressure effect. But you see here a little bit of pressure dependency, but not much. And that's probably due to the fact that I'm building up this oxide on the surface, and it's changing the characteristic, the ability to vaporize, and changing the system from a vapor phase reaction to more of a heterogeneous reaction. Now, what happens if I burn the aluminum in different types of oxidizers? Okay, this is an example of, suppose it was to react in a mixture that had fluorine. Fluorine is isoelectronic with hydroxyl radicals. So fluorine is very reactive, okay, like the hydroxyl radical is with the aluminum. And what you see here then is on the left, this is a situation where the aluminum is burning in an SF6 environment. So essentially, mostly pure fluorine. And note that as this particle falls, there's no smoke cloud at all. In fact, there's no condensed phase species in the products being formed. And that's the reason for that is thermodynamically, I've now driven the products to ALF3 gaseous. Okay, and if you were to quench the particle on the silica wafer, what you would see is essentially an image of a particle without any condensed phase material. It's like a mirror image. So again, there's different ways to change the characteristics. You know, a lot of times, the fluorine, as I said, it's being isoelectronic with OH. People will add fluoropolymers with aluminum. And what's been also observed is there's a reaction with the fluorine that will actually reduce the oxide layer itself. So at very low temperatures, you can start a very slow exothermic reaction that removes the oxide layer, and then you get the fluorine can go directly to the aluminum itself, which would be a very fast reaction. Okay, so I want to say a little bit more about just general characteristics of particle combustion. I talked about a situation where we have this vapor phase diffusion flame, where I have a gas phase flame standing off the distance of the surface of the particle. And in those modes, it's basically diffusion controlled. So what I have is something as shown on the left here, diffusion controlled flame that has this envelope. So again, schematically looking at the surface here, going far away, the fuel is vaporized, say, it diffuses out into the flame front, oxidizer diffuses in, they meet where their mixtures near stoichiometric, and that's where the temperature will be the maximum. And because the temperature is high here, it diffuses back towards the surface, and that heat is used to vaporize the aluminum. Okay. And the products are obviously a maximum here. They'll diffuse to a certain concentration to the surface and diffuse outward. Now, I can also have a situation where if I have a large particle, the system still is diffusion controlled, but without the envelope flame. Okay, and what's limiting the process, again, is essentially diffusion of oxidizer to the surface or products away from the surface. And the reaction that occurs at the surface is much faster than the diffusion process. Okay. And under those cases, then I'll see an elevated temperature at the particle surface. Now, if I go to a situation which I refer that the overall reaction is kinetically controlled, okay, then I'm going to basically have likely a surface reaction that's slow. Okay, and as a consequence of that, the oxidizer is going to diffuse very quickly to the surface. The products are going to diffuse very fast away from the surface. And if mass is diffusing fast, that means heat is also diffusing fast forward and backward to the surface. So as a consequence of that, even though I have an exothermic reaction on the surface, that heat will likely be diffused away very quickly, and the particle will essentially burn in whatever the ambient temperature is around it. So if the ambient temperature is 2,000 Kelvin, that'll likely be the temperature of the particle then. Okay, and you can go through and do an analytical analysis, and that I give the information on how these equations were obtained in that last set of notes. But you can look at diffusion versus kinetically controlled and calculate what the characteristic times are for burning of the particles. So the top two equations are diffusion controlled combustion with vaporization or a surface reaction. So they would have been the two cases on the left that I showed you in the previous slide. And what I find then is the burn time for diffusion controlled is proportional to the particle density and the initial diameter squared, okay, divided by rho d. So you can see here, here's the rho d. The pressure term cancels out, log of 1 plus the Spalding B number. Okay, and the Spalding B number is basically determined from sort of your spatial end conditions in the problem. And if I had a situation where I had a surface reaction, but again, it was diffusion controlled, I would again find that the burn time is proportional to the initial diameter squared. Okay, so if I look at the third case on the right of the previous slide where the reaction at the surface is kinetically controlled and the diffusion is fast relative to that surface reaction, then I'll find the burn time is proportional to the diameter to the first power. Okay, and in addition, I'll have the surface reaction rate constant here, which is temperature dependent. It'll also be then dependent on how much oxidizer I have in the system itself. If I take the ratio, for example, of this term and this term here, I can sort of define a Damkohler number. And if I set this Damkohler number, say, to unity, then I can use it to see when the system may change from a diffusion-controlled system to a kinetically controlled system. Okay? So if the particle diameter is very large, then the diffusion time is large, and the kinetic time is small, so it's going to obviously be diffusion controlled. If the pressure is very large, the same result. So at low pressures, it'll be kinetically controlled. At high pressures, it'll be diffusion controlled. Okay, so here's some results then of burning times. And the burning times are here plotted times the concentration of oxidizer and the ambient around the particle versus particle diameter. And what you can see then is as I decrease the particle size, drawn on here is what the burning rate should have looked like for time in terms of a d squared law and a d to the 1 law here. So, and you can see the data, although there's not very much data at larger particles here, it gives the idea that it's going to switch. And you notice then if I go to a higher pressure, the diameter where that occurs basically decreases. So here's the same plot now for aluminum particles. And what's shown here then is the d to the 1.8 was a correlation of all the data in the literature. And so it's not quite d to the squared. The hypothesis there is that the oxide layer is changing the available surface area for the vaporization of the aluminum going out into the surrounding environment. And then I get to a point then, notice where the slope changes. So you'll see a couple lines here where as I go to smaller diameters, and the transition is all about in the range of maybe 10 to 20 micrometers. But now the environment is at two different temperatures. So if the environment is basically at a lower temperature, that means if it's kinetically controlled, the kinetics at the surface are slower. So the burning time should be longer, right? And that's what's observed here then. And if I raise the surrounding temperature, the burning time is decreased. Now, one thing I'm not showing here is these slopes that are approximate through this data are d to the 0.3. And I'll come back to that, but that's much lower than theory would predict. So one of the questions is, why is that? As I go to smaller diameter particles, this is looking at the effective diameter on aluminum particle ignition. So if I'm in the diffusion-controlled regime, very large diameter particles, what I notice is that the ignition temperature is about 2300 Kelvin. So the 2300 Kelvin is the melting temperature of aluminum oxide. So for these larger particles, what it's saying is until that oxide melts and is free to move on the surface, there's different surface tensions of the molten aluminum, which melts about 930 Kelvin, and the molten oxide on the surface, which is going to start moving around, and the surface tensions will be different. The aluminum oxide will start forming what looks like a lobe and open up some free surface. Until that happens, I don't have ignition for large particles. However, as I start going to smaller particles, note that the ignition temperature starts to drop off. Okay. And there's been different theories as to why that has happened, and I'll kind of go through a couple of those. Okay, so that's a general characteristic of large particle burning. Again, the question is whether or not it burns in the vapor state or heterogeneously, and if the flame temperature is going to be limited by the dissociation temperature of the oxide. I didn't show anything on boron, but again, one of the problems with boron particles is if I have a boron particle here and I have an oxide on the surface, the oxide, remember this doesn't melt or vaporize rather. TB here is about 4,000 Kelvin. This is TB here is about 2,300. And so what has to happen is I've got to basically heat up the boron to remove this oxide so that oxygen can quickly get to the surface. And that takes a long time. And so ignition delays of large particle boron can be long. And so again, people are looking for ways to, how can I reduce that oxide layer? If I add fluorine again, the fluorine will reduce the oxide layer and form oxyfluorides, things like OBF, that will assist in the removal of the oxide layer at lower temperatures. So really, boron has been thought to burn in two stages. The first stage, where the particle's heating up, there may be some interfacial reaction here, growing more oxide, until I get to a high enough temperature that I remove all the oxide. And then there's a second stage referred to as a clean burning stage of boron. Now, the other problem with boron is to get all the energy out of the system, you would like to have it form B2O3 liquid. The problem is if I look at what's going on in the gas phase, instead of forming B2O3 liquid, if there's hydrogen around, what I form is a species called HOBO. Okay, and for me to basically convert this HOBO to B2O3 liquid, as I'm, for example, if this was used in a rocket motor, as I'm expanding in the diffuser of a nozzle, as the temperature's going down, this process becomes kinetically limited. And so a lot of times I can't recover all the expected energy out of the system. Okay. Okay, so as I said, there's quite a bit of interest then in going to nanoparticles and what they can offer in terms of energetic materials. So here were some of the original ideas of what the nanoparticles could offer. Shorter mixing times, what I mean there is the length scales are smaller, so diffusion times are going to be shorter. Reaction, because of an increased surface area, I'm going to have larger surface area for reaction. Smaller thermal capacitance, right? The particles, as I said, you're starting to see the particles have to be heated up to a certain temperature for either vaporization or melting for things to happen. And so if the total volume mass is less, then I don't have to put as much energy into the particle to get it up to those temperatures. So that response time is going to be quicker. It'll have an increased specific surface area, which means if it's a heterogeneous reaction, I'll have a more area within many particles to consume the material, which results in increased reactivity. Nanoparticles have shown increased catalytic activity. If you look at gold particles at the micron scale, they're basically not a catalytic particle at all, but if I take it to the nanoscale, a gold particle becomes a very good catalyst particle. They end up having lower melting temperatures, and a negative aspect is a lower sintering temperature as well. I mean, the idea behind this is that if I look at a nanoparticle, because of the surface to volume ratio, more of the atoms are on the surface. And the atoms that are on the surface have a lower coordination. So in other words, they have dangling bonds that are not connected to another to complete the bonding. And that shows up here. So if I look at basically the number of surface atoms versus the number of bulk atoms, this is for iron crystals. You can see as I start getting below 20 nanometers, the number of surface atoms increases relative to the number of bulk atoms. And so the particle starts overall having characteristics of the surface atoms versus the bulk atoms. And as I said, they have a lower coordination. Effectively, they have a higher energy content then and can become more reactive. Just to show you some examples of that, how it can affect some of the properties. Here I'm looking at tin nanoparticles particles. And you can see as I decrease the particle size, the melting temperature starts going down. Again, I've got to get probably close to 30 nanometers or so or below. And on the right, the heat of melting also is going down. So less energy is required to either melt the particles or it'll happen sooner because I have a lower melting temperature. And the same characteristics occur for aluminum itself and aluminum oxide. So if I have a small aluminum particle, I'll see the same characteristics, and it'll also be true with regards to aluminum oxide. Now, I mentioned, one of the problems was the lower sintering temperatures. So you can imagine now if I have nanoparticles that are in a matrix of a binder and they're in close proximity, as the thermal wave starts propagating down into the material, if those nanoparticles are in close proximity, the temperatures for sintering are lower. So if the nanoparticles start to sinter, then I'm losing surface area, okay? And I'm starting to approach, again, a micron-type behavior versus a nanoparticle behavior. And this is another interesting result. I'm not sure it's been totally verified, but the size affects both the metal and the metal oxide properties. So on the left, I'm showing what happens if I consider 3 different types of reactions, where I take nano-aluminum and it eventually forms nano-aluminum oxide, versus taking bulk aluminum and forming bulk aluminum oxide, or taking nano-aluminum and having it form bulk aluminum oxide. And notice that if it forms the nano-aluminum oxide, as the particle diameter got small, the overall heat of reaction is less. Because the problem is in the aluminum oxide, I still have a lot of surface atoms that have all these dangling bonds. So I haven't captured all the energy release. Whereas if it formed if the nano-aluminum went to the bulk aluminum oxide, I actually get an increase in the heat of reaction, because I start off with a nanoparticle that has this excess surface energy and forms bulk oxide particles which don't. And that shows up then in that plot on the right here as well, the characteristics of how the heat of reaction changes with the fraction of surface atoms with dangling bonds. Another effect that one has to consider as the particle size gets smaller, typically on all metals, to prevent them from basically being pyrophoric, they have a naturally passivating oxide layer. So if I have an aluminum ladder and I scratch it, I'll basically remove the oxide layer, and locally I'll have an oxidation reaction. But because I have a lot of aluminum around in the ladder, any of that heat release of that reaction quickly conducts into the ladder and you don't know it, okay? But in the case of smaller particles, that oxide layer can become significant relative to the amount of aluminum, and as a consequence of that, reduce the overall energy content of the particles. So you have a naturally occurring layer, say on an aluminum particle, maybe of a small nanoparticle, maybe 3 to 2 nanometers. And this plot basically shows then, as I decrease the particle diameter, what the remaining energy content is in the particle, because now more and more of the particle is oxide versus the pure aluminum in the core. So if I get down to something like, this is a micron, so here I'm maybe 50 nanometers, you can see that 50% of the energy is lost because I have a relatively thick oxide layer surrounding a core of aluminum. So immediately one of the questions as people started working with this is, if I keep going to these smaller and smaller particles, I've got to do something about removing that oxide layer. Otherwise, I'm losing all the advantages of adding metals to my energetic materials. Okay, there's also another important length scale to consider as one goes to nanometer particles. And this is the fact that one needs to consider now the mean free path length, which is basically asking the question is, what's the diameter of the particle between the typical spacing of molecules and the surrounding gas? Right, the assumption is when I have a large particle that the density is such that I'll have a lot of collisions with the surface, and I'll be able to differentiate then the particle from the surrounding collisions in the gas phase. But if I get to a small enough particle, it'll start looking like a molecular species itself, right? And the collisions that happen at the surface will be fewer and fewer statistically. So another length scale of importance to the combustion of small metals is the mean free path and the surrounding gas phase. A comparison of this length scale to the particle diameter defines whether continuum conditions exist. That is, whether or not the particle may be distinguished separately from the gas molecules. The key dimensionless group that defines the nature of the surrounding gas of the particle is the Knudsen number. So you can see here the Knudsen number is defined as 2 times the mean free path over the particle diameter, where the mean free path is, from kinetic theory, is defined as 1 over the square root of 2 times pi times the molecular diameter squared divided by the gas concentration. And that can be modified from kinetic theory to as it's shown in the last equation, where I introduce the viscosity, the pressure, molecular weight of the gas, and the temperature of the gas. So now you can see how essentially the mean free path will vary with pressure and temperature in the environment. Okay, so where mu here is the gas viscosity, mw is the molecular weight of the gas, and so at atmospheric pressure, particles of 100 nanometer and smaller are characterized by Knudsen numbers greater than unity for the entire temperature range from room to combustion flame temperatures, indicating that they can no longer be considered as macroscopic particles in a continuum gas. Okay, so now you're basically getting to a situation that looks like a rarefied gas. Okay, so if you're doing modeling of nanoparticles, which many people started off in the beginning, they just treated them as continuum particles. But what it does, though, is it affects the kinetic rates. It affects the energy exchange at the surface, the mass exchange at the surface. Okay, and it can be significant depending on the size of the particle and the surrounding environment. So for Knudsen numbers of the order 1, expressions used to model heat and mass transfer in the continuum limit are no longer applicable. Appearance of a discontinuity in temperature, velocity, and concentration profiles at the gas surface interface are often referred to as a slip or jump condition. Okay. The magnitude of the slip depends on the efficiency of the exchange of energy and momentum between the gas and the surface. The efficiency is quantified in terms of accommodation coefficients, alpha here, of a gas surface interface. For example, the thermal accommodation coefficient is defined as basically alpha sub T here, which is a function of the surface temperature and the gas temperature, which is equal to basically the temperature of the gas after the scattering from the surface minus the temperature of the gas divided by the surface temperature minus the temperature of the gas. And those accommodation coefficients can be very small. Okay, and knowing the accommodation coefficient, then I can evaluate what the convective heat transfer would be in terms of a heat transfer coefficient. And I give an example here of what that is. Okay, so here the heat transfer coefficient is the thermal accommodation coefficient times the pressure times the speed of sound times the ratio of specific heats plus 1 divided by 8, the temperature of the gas, the ratio of specific heats minus 1. Okay, now that's an interesting result because now if I have a very small particle and I have a problem, I'm not very efficient in exchanging heat with the surroundings. So in other words, a gas molecule comes in, hits the surface, and if the particle's reacting at the surface, the temperature of the particle is going to go up very quickly because of the low specific heat of the particle, the small size of the particle. And how's that heat then removed from the particle? if the collision process is not very efficient to remove the heat itself. So in these cases, you might even see an increase of temperature of the particle relative to the surrounding, even though the particle is very small. So here, experimental measurements of thermal accommodation coefficient suggest that the values at elevated temperatures for some systems are the order of 0.1, and some may be much smaller. As the Newton number increases, heat and mass transfer are reduced significantly by non-continuum effects. In the kinetic limit, transport of mass and heat for a Lewis number approximately 1 is rapid, and the concentration and temperature profiles are relatively flat, but that's not going to be the case potentially if I'm in this rarefied gas limit. However, for isolated burning of nanoparticles, particle temperatures can rise hundreds of degrees above ambient during combustion at elevated pressures, while for lower pressures, the temperature overshoot as well as the combustion rate can be reduced. These observations suggest that although the Newton number is greater than 1 for some nanoparticle systems, the combustion has not reached the kinetic limit due to the inhibited transport and the non-continuum regime. Such particles can be considered to be burning in some transition regime between the diffusion and kinetic limit, in which neither the d squared or the d to the 1 burning rules apply. Okay? Okay, so let me go through this slide and then we'll take a break. What you generally find, remember if I said overall, if I have a small particle and the bulk around it, the heat and mass transfer are going to be fast. So even though the temperature at the surface potentially could go up of a nanoparticle, it's still going to be very close to that of the surroundings. And unless the surrounding temperature is above the vaporization temperature of the metal, in the case of aluminum, I'm not going to be vaporizing aluminum. And the vaporization temperature of aluminum at 1 atmosphere is 2,700 Kelvin. So if I'm burning these particles in a combustion system where the temperature is only 2,500 Kelvin, then it's highly likely that the particles are going to be burning close to that temperature. And as a consequence of that, they're not going to be vaporizing, right? So all of a sudden, that's going to, the nanoparticles turn in, no matter what condition, I'm going to be burning them heterogeneously, independent of pressure. So what happens now? So the oxidizer comes down to the surface. It wants to react with the nanoparticle, and it wants to form aluminum oxide, right? But aluminum oxide doesn't vaporize until I get up close to 4,000 Kelvin. So I form the oxide right on the surface. So as this combustion process occurs, more and more oxide is just gathering on the surface. And so the idea of how a nanoparticle might burn is indicated by basically what's referred to as a shrinking core model for a spherical particle of unchanging size. So now what I have is something that looks like this on the left here, where this is the original particle. It had this original oxide layer, and oxidizer is going to come to the surface, and now the oxidizer has to be transported across the oxide layer, or the aluminum has to be transferred across the oxide layer. And what happens then is effectively it looks like the reaction zone is shrinking because the aluminum particle is shrinking in the condensed phase, and the oxide layer is just getting thicker and thicker. Okay, so now the question comes about is, I originally thought these particles were going to be kinetically limited at the outside surface. But is that the case anymore? Because now if I got to diffuse the oxidizer or the fuel across that thick condensed phase oxide layer, can that diffusion process start limiting the burning process instead of the kinetic process again? Or is it kinetically limited here at this interface? So now I've got another set of conditions to look at where the combustion process is being controlled. And that's what a shrinking core model does. So you can see on the right here, the bottom case here is the chemical reaction controls. So what's slow is the reaction rate here. Diffusion across this oxide layer is fast. And I'll get a concentration profile, for example, of the oxidizer in the condensed phase that looks like this. I get to the reaction zone, and it's immediately consumed because the reaction's fast. If that's not the case, and it's the transport that's limiting it, then I'll get profiles that look like shown at the top here, where now I have a diffusion-controlled process, and the oxidizer goes to essentially zero at the interface where the fuel is. Okay, so the same sort of thing that one would expect in the gas phase is now happening in the condensed phase. And if you go through theory, I'll stop here. If you go through theory, what you find, if it's diffusion controlled in the condensed phase, it's still dependent on the overall diameter or radius of that particle squared, the time for burning. If it's a chemically controlled reaction, the time for burning is basically the diameter to the first power or the radius to the first power. Okay? Okay, so let's stop here, take a 15-minute break.